All right, today we are talking about electronegativity. And what it's really all about is atoms that are bonded together and one of them is greedier than the other. So just like a tug of war. So we're going to talk about what it is about certain atoms that makes them greedier. Okay, so again, this word electronegativity means the ability of an atom while it's in a bond to attract electrons to itself. And there was a little activity in the book, a comic strip, where it showed a polar bear stealing the ice cream away from a penguin. So the ice cream is the shared electrons. The most electronegative element of all is this big polar bear in the upper right. That's fluorine's spot. Fluorine really wants to get one more electron. It's small, so it only has 2 shells of electrons, and so its positive core is right there with not much shielding, and so it's very greedy. The noble gases, by the way, don't really count as having any chance at having an electronegativity because they don't form bonds very often. Electronegativity is arbitrary as far as what the number is. So the highest is 4 or 3.98 and the lowest is 0. You can see all the noble gases, helium, neon, argon, all of those are 0. And metals, the left side here, have much smaller numbers than nonmetals over here, the right of the zigzag, which makes sense, right? Metals don't even mind giving up their electrons, while nonmetals would really like to get more electrons. We can actually use electronegativity to help us figure out if you've got a nonpolar bond or a polar bond. And we're only talking about nonmetals here, covalent bonds. It can also help show you that certain bonds are ionic, and remember those are between a metal and a nonmetal. And those are not sharing electrons. Ionic bonds actually have the nonmetal completely taking the electron from the metal. So that's quite different from these covalent bonds where they're sharing electrons. So what's the difference between polar and nonpolar? So check this out. Haha, polar, nonpolar. There are my bears there. A polar bond is where it's not an equal sharing of electrons. One element is stealing part of the other one's electron cloud. How rude, I wrote. So here the fluorine is greedier. It has a larger number on the electronegativity scale, 3.98. Hydrogen's is only 2.1. So you can see this weird little S kind of a symbol. It means partial. It's not taking hydrogen's electron completely away, but it is taking part of its electron cloud, so it gets a partial negative charge. And then the opposite happens with the hydrogen. Since its positive proton core is being more exposed, now that the electron cloud is being taken away, it's left as a partial positive charge. A nonpolar bond is when you have a perfect equal sharing of electrons. So maybe it's a tie, like a fluorine and a fluorine, or maybe you've got 2 atoms that just have very similar electronegativities. They don't have to be exactly equal, but you know, one isn't very much higher than the other. Alright, let's go back to the electronegativity notes. So let's go through each of these. Nonpolar again means the electrons are shared equally. So here's a picture of 2 polar bears that are sharing equally because they're both oxygens. There's 4 scoops of ice cream because that's a double bond. And here's 2 hydrogens sharing their ice cream equally. So remember I was saying that the difference doesn't have to be exactly the same, or the difference doesn't have to be 0, I should say. It's usually smaller than 0.5. So for example, if there is a bond between a phosphorus and a hydrogen, if you look up their electronegativities on that chart, 2.19, 2.1, the difference is only 0.09. That's a nonpolar bond. So let's find some more examples. If we go to our electronegativity chart here, remember that you can only choose things to the right of the zigzag, okay? Not to the left, because as soon as you are incorporating a metal, you're talking about an ionic bond. Covalent bonds are nonmetals. So let's look for ones that have a pretty close difference here. So nitrogen 3.04 and oxygen 3.44, they would form a nonpolar bond because their difference is only 0.4. How about carbon 2.55 and sulfur 2.58? Their difference is only 0.03. How about hydrogen? Remember, even though it's to the left of the zigzag, it's still a nonmetal, 2.1, and carbon 2.55. That's only a difference of 0.45. So that would also be a nonpolar bond. All right. How about polar bonds? Now we're talking where the electrons are not shared equally. Check out this picture of the polar bear stealing the ice cream cone from that penguin. The penguin is the weaker nonmetal atom. So the negative side is always going to be the side that has the atom with the larger electronegativity. Because remember, that's the greedy one that wants to steal part of the electron cloud. The other side is always left more positive, so the one with the smaller electronegativity. Example, how about carbon and chlorine? Two nonmetals, their difference is 0.61. So this is not a perfect range, but if the difference in electronegativities is somewhere between 0.5 and 2.1, now that's an unequal sharing. So let's go back to our chart and see if we can find a couple more examples. How about carbon and fluorine? That is bigger than 0.5, so that would be an unequal sharing. How about, let's see here, hydrogen and chlorine, 2.1, 3.16. That chlorine would have a partial negative when it's bonded to that hydrogen. How about silicon, Si, and bromine, 1.9 and 2.96. That's another one that would be a polar bond. Another word for polar is dipole. It means two poles. And if you look at a polar molecule, one side of it is partially positive and one side is partially negative. That's why it has two charged ends, two poles, dipole. Finally, ionic bonds, that's when one atom completely takes an electron away. It's not sharing at all. This happens when there is a huge difference in electronegativity, such as the difference between a metal and a nonmetal. Metals have low electronegativities, so they don't have very much of a grip on their electrons and tend to lose electrons. Nonmetals are the opposite. They have high electronegativities. They're more likely to take electrons from the other atoms. This makes sense if we look at this chart again. These are the nonmetals to the right of the zigzag. All these numbers are big, 3.44, 3.98, etc. Metals are to the left. Look at, most of these start with a 1. So it's not always true, but typically ionic bonds have a difference in electronegativity of 2.1 or higher. Example, the metal potassium and the nonmetal fluorine. The difference between those two is 3.16. And you can easily find more examples on here by picking something to the left of the zigzag, like lithium, 0.98, and something to the right of the zigzag, a nonmetal, like fluorine, 3.98. That's a difference of 3. Alright, last couple things here. Again, this is not a perfect set of ranges here, but it gives you a pretty good idea of when something's nonpolar versus polar versus ionic. So there are actually two ways that something can be nonpolar. One is if, like we already discussed, the two atoms have pretty much equal electronegativities. Nothing's winning, like between two nitrogens. But there's another case where if polar bonds cancel out, that's also a nonpolar molecule. So example, carbon dioxide. It's a linear molecule because there are no lone pairs on the central atom. One oxygen is pulling to the right, one is pulling to the left, equal and opposite, so this is nonpolar. Even though technically it looks like there would be polar bonds within it, they cancel out. There's no net charges. So for a molecule to be polar, there needs to be an overall pull of the electrons. And shape really matters when you're trying to figure this out. That's why we've spent so much time talking about shape. So there's a little practice here that we did in class, so let's do this now. We're supposed to figure out if each of these molecules that I've got here would be polar or nonpolar. So let's start with CH2O. So I'm going to draw this guy. The electronegativities are 3.44, 2.55, 2.1, 2.1. So let's look at the carbons and hydrogens first. The difference here is 0.45. That means there's an equal sharing between the carbon and the hydrogens. Uh-oh. Carbon's 2.55, oxygen's 3.44. Now that is a difference of 0.89. That means that the oxygen is winning. So we're going to draw a dipole arrow. You always point the arrow at the greedy atom. So the oxygen is greedy because it's a bigger number on the electronegativity scale. That means this oxygen is going to be partially negative because it's stealing part of carbon's electron cloud and probably kind of stealing part of hydrogen's too. So this side of the molecule is left partially positive. So would this be polar overall? Yes. Those bonds, or that pull, is not being canceled out in another direction. How about CCl4? Let's put carbon in the middle, all our chlorines. This would be a tetrahedral shape. Oops. Chlorine, that's a chlorine too. Oops. Trying to draw my lone pairs in. Chlorine is 3.16, I believe. Carbon is, 2.55. That's a difference of 0.61. So the chlorines are winning. However, there's a chlorine pulling to the right, there's a chlorine pulling to the left, there's a chlorine pulling up, there's a chlorine pulling down. This is like you went on a walk. You went a block north, you went to block east, you went to block south, you went to block west. Where'd you end up? Exactly where you started at. So this would be a nonpolar molecule because there's no net pull in any one direction. All the pulls cancel out. Now I made it seem like this was a two-dimensional molecule. In 3 dimensions, even with the tetrahedral shape, those pulls still cancel out. Finally, we've got F2. F is the most electronegative, but if there's 2 of them, neither side wins. They both have an electronegativity of 3.98. So they're going to have an equal sharing of electrons, just like CCl4. Also, there's a handy-dandy little flowchart that I made, how to tell if something's polar or nonpolar. So first you have to double check that it's nonmetal atoms. If it's not all nonmetals, then you've probably got an ionic compound or a metallic alloy. So first you have to check that. Then if you know it has all nonmetals, you see if the molecule has an atom or atoms that are greedy, meaning they're more electronegative by 0.5 or higher than other atoms that they're bonded to. If yes, you're still not done. You have to draw your molecule in 3 dimensions, add arrows that point to the greedy atoms that are stealing more than their share of the electron cloud. If they cancel out, it's nonpolar. If not, it's polar. Okay, and there was another way back up here. If you don't have a greedy atom, then it's nonpolar automatically. Alright, that should help you